Hi, everyone. Thank you for coming. I'm very excited to introduce Alex, Chen, and Zach Lee today. Alex is the CEO and founder of Nexa AI with a PhD in mechanics and computation from Stanford University. He's a serial entrepreneur, served as the president of the Chinese Entrepreneur Organization, and is also a gold medalist and mathematics Olympiad. Zach is the CTO and co-founder of Nexa AI and has accumulated years of experience in on-device AI at Google and Amazon Lab 126. And he received a master's in operation research from Stanford University. And Alex and Zach, as I said, are the founders of Nexa AI and have authored the Octopus-series models. Nexa AI builds lightweight and powerful multimodal models for AI agents and provides on-device SDK infrastructure to make models run fast and energy efficiently. So without further ado, I'll pass it on to Alex and Zach.
Thanks, Abel. Yeah, so it's been very honored here to share you guys about our recent work about how to use the algorithm of functional token to enable on-device AI agent. And today we will share our recently for research work. We will demonstrate our demo first and then explain the algorithm and the research behind our model. Zach, would you like to say hello to everyone here?
Yeah, hi. Thanks, Alex. Hi, I'm Zach. I'm the CTO and co-founder of Nexa AI. I've been working on device AI at Google and Amazon.
Yeah, sounds good. So I'm going to share my screen, and we prepared slides. And feel free to interrupt us when you have any questions. And we'll also have a question and answer session after the presentation. Okay, can you see my screen? Okay,
Yeah,
so
we can see it.
the topic we are going to discuss today is the functional tokens for on-device multimodal models. So I guess thanks for the intro. So we'll skip the introduction of ourselves. And to understand what we are doing now, we like to play one demo video to show the capability of our model. Basically, what you can do is like we imagine the future of device is like there is a smart assistant inside your device and it runs totally, local. It runs locally. And also like it can not only, taking your a text command, which is like a natural language command, but also the image you send it to. And then it can combine the information of both your text input and image input. In the future, we may incorporate audio and video as well. After that, the model can take an action based on the input information. So let's see how it works in the in a app created by our model. So this is our latest model called Octopus v3, and it is a sub-billion model. That means the number of parameters is less than 1 billion parameter. And let's see how it works in a demo app we created. So let's see if we want to do a Instacart purchase, you can send the image of the product you want and then use a natural language like order to for me. What it did is like it will trigger a function called Instacart shopping, and it will recognize this is the image. This is a pineapple and you want to order two. After you send this command to the to the system, it will jump to the Instacart app and then execute the command. Let's see another example. Imagine that you are now, is hiking around, Golden Gate Bridge and you want to search the history of Golden Gate Bridge. You can just take a photo and then tell me history about this image. It will trigger another function called Google search. And then it will jump to the Google search and find the result. Similarly, if you want to purchase another product on Amazon, it can, execute the command as well and very fast. Let's see another. there is a question. Please go ahead.
Thank you. So this is Keith Burkhardt. A question I had was, when you have an image and maybe the AI incorrectly interprets the image, how do you deal with that? I mean, for example, that pineapple is very obviously pineapple, but what if you accidentally try to take a picture of a pineapple and there was a computer in the background, and suddenly Instacart orders two computers, which is a very substantial mistake. How do you avoid those mistakes from happening in a new updated model? I know this is just a demo app.
Oh, that's a great question. So, firstly, this model can take in both text and image, and when we process this image, I mean, it's actually a multimodal way, like we tokenize the image. So the model, taking the whole information. So when you say like, I want to purchase, I want to purchase this fruit. I mean, even though there are both pineapple and the computer, it can recognize like you want to purchase this, pineapple. But if just say like I want to purchase this, and there are two products inside the image, then of course, I mean, there will be, it may, choose, a more like possible product, maybe the one like take up the most of the image.
I see. Thank you.
Yeah. So let's see this last example. This is a very good example to demonstrate our model's capability. We actually send an image here. There is a text inside the image called "the error of on-device AI agent is coming," and note that our model don't have a it's an end-to-end solution. So it's not like do image caption first and then pass the caption to the language model and get the output. It's an end-to-end solution, which means like we tokenize this image and send everything into the model. And our model can recognize the text information inside this image. And our model is only, less than 1 billion parameter. Let's see how it works. We can say like send an email to dev at Nexa for to hello@nexa4ai.com, and then we say like set the title, and also we say like the information should be short and capture the main idea. So if you look at the main body for this email content, it actually capture the idea of this image and capture the text like the error of on-device AI agent is coming very well. So that's our demo, and what our model can achieve in your mobile phone or laptop or VR glasses. Next, we will discuss the model behind it and what kind of algorithm we use for it. Okay. Again, like if you have any question, feel free to interrupt me. Yeah. So firstly, I'd like to introduce a little more about the background of small language model and especially the agentic development for that. Small language model begin to get much more attention since Apple's WWDC. But we actually start this journey a long time ago. So recently, the evolution of small language model have seen significant contribution from leading tech companies. For example, we've seen Microsoft's 5.3 and Google's Gemma 2B or 7 billion model, and also Google's Gemini Nano. At the same time, function calling is always a very interesting topic since it's the cornerstone for AI agent. And we've seen the innovations from like Nexa's Flow, their model Nexa's Raven and Toolformer, this kind of fine-tuned model that can perform much better than the pre-trained version of open source model. That we also noticed phenomena that for models that is less than 10 billion parameter, it is very hard to get a accurate function calling results. And if you want to deploy this small language model on your device, it actually cannot be too big. Otherwise, there is battery issues, there is latency issues, and most importantly, there is RAM issues, which means like if you want to run this model on your device, the chip must be large enough. And at the same time, we've seen many consumer product coming from AI agent, for example, the Rabbit R1 and Human AI Pin. And actually, we've noticed a lot more, this kind of AI hardware coming. I think we can expect them at the end of this year, and maybe next year there is a burst of AI hardware, mostly like earphone and AI glasses. So then I just mentioned like the accuracy of on-device AI model. When we say on-device AI model, we actually have an internal threshold that is all model less than 10 billion parameter can be classified as on-device AI model, because we can still figure out a way to deploy this kind of model. But the function calling accuracy is still very low. As you can see, it's actually less than 60%, just around 50%, and that's far away from the production requirement. And additionally, we want this language model as small as possible, because if you need to run a language model on edge device, it's actually power intensive. And for example, like one research found like if you use 1 billion parameter model to output one token, the energy consumption is 0.1 joule. And for iPhone, typical iPhone will offer usually like 50 kilojoule energy inside the battery. That means in a typical agent call, which means like we pass all the function description in the context and then take action, it can only support you around 70 agent call, and that's obviously not ready for the production. So we proposed an idea of functional token. Next, I'll discuss more about the research behind our work. So to figure out how we get the function calling correctly, let's look at the fundamental mathematical formulas to express that. Basically, you want to take in the user's query in Q and then output the correct function f. That's the function selection stage. And imagine like you have one model as pi 1 to help you do that decision. And secondly, after you get the user's query in Q and you have already decided which function to use, then you need to generate the parameters for this function. So imagine that you have another model called pi 2 to make that generation. Our idea here is like we actually can use a unified model strategy. That is, we can say pi 1 equals pi 2 equals pi, and we can redefine the objective here, which is like you have the user's query in Q, and now you need to select the correct function f, and then you need to generate the parameters. And of course, you can do a very a straightforward split of this probability expression, and it becomes the two-way. That is, you use one model pi to get the function selection first, and then generate a parameter. So the idea here is like among all the previous function calling way, including GPT-4, what they do is like imagine you have 20 functions to choose from, and then you take in the user's query. The way to do that is like you put all the function description inside the context, and the language model needs to understand these are all 20 functions description, and then it's taking the user's query and output the result here. So our idea is like, when you need to use a natural language to express a function, why not use one single token to express that function? And, for language model, especially smaller language model, it's hard to understand a long context. And usually 20 function description can nearly, exceed the context length of your model. And when the model needs to, process that kind of long context, it becomes really slow. And when it is on device, it's also, power intensive. So why not get rid of all these contexts? So that comes to our idea, which is called a functional token. The idea behind this is like we want to, kind of embed each function, including its function description, description of arguments into one token. And the idea is like we incorporate some special token. As you can see, this is Nexa 0, blah, blah, to Nexa n-1. These are some special tokens that have never seen before by the language model. So if we look at the hidden embedding of your transformer model before it is entering the decoder layers, it's basically the token embedding, or initially like vocabulary. You basically convert that into token embedding, and then they are entering the decoder layer. We can extend that linguistic token space, and we call it called functional token space, and then we can use that space, that in kind of embedding, to encode this function description. And we also prepared a kind of training dataset template. It's actually very straightforward. You just need to give the query, and then you provide the function description after the response. So in a real production use case, the user can only they just need the result between this response and before the next end. So during a production use case, you can use Nexa end as a stopping criteria. So the model can take in the user query and output the command directly. So there is no any like function description. And for each agent call, like I said before, if you put all the function description inside the context, that needs over 1,000 token. Now you can just generate the functional token and the parameter along with it. So that's just like 20 to 30 tokens. And I mean, mostly like even much lower than that amount. And that's why our model becomes very fast and energy efficient. And surprisingly, we found like this way can deliver a really, really accurate function calling accuracy, even higher than GPT-4. So the idea is like we can transform the prediction task for function names into a single token classification among the n functional token. And yeah, this image just demonstrates the idea of for this functional token. I mean, taking the use case on mobile phone as example, on mobile phone, you may need different kind of functions like turn on the YouTube video, search something on YouTube video, search something on Google, and set alarm, this kind of different API. And what it did is like, I mean, the previous state of the art way is like, you taking users query, and then we based on this query to do a rag search, maybe find some relevant function description, and then send all of them to the context. After that, it generated the response. So this is the previous way. Now we can just take in the user's query and output the response. So that would be the difference from the previous way. And we've seen very good results for our model called Octopus V2. We can now enable a 2 billion model to achieve GPT-4 level function calling accuracy. As you can see here, our model, when it is deployed on your mobile phone, I mean everything everything locally, that will show how our model really run a real mobile phone later. And our model, when it is deployed on your mobile phone, the latency is still like around 5 times faster than GPT-4. I mean, imagine GPT-4 is actually a cloud model with hundreds of GPU, behind it, and compared to using the same configuration and same task compared to Llama 7B plus RAG solution, we are 70 times more we are 35 times efficient. Like our speed, the inference speed is 35 times faster. This is because our model is smaller, and our context, the number of tokens that we need to process is also, is also much lesser than the Llama 7B plus RAG solution. And as you can see, our accuracy is almost like it's basically like averagely over 95%. And we already provide our model to many customers like hardware company. We are now, in collaboration with many big hardware company, laptop or mobile phone as well. Yeah, so that's the part of one use case of Octopus V2. You can actually search Octopus V2 on Google, Twitter, or LinkedIn. I believe there are many posts from scientists to explain more, about the algorithm behind our model. And also you can have a try of the model HuggingFace. Yeah, our model has ever ranked, second place HuggingFace among all open source models. It's been pretty popular and have many comments in HuggingFace as well. So the next work I like to share is still using functional token, and in this work we call it a graph of a language model, and we actually envision a edge cloud collaboration in this paper, and actually that's also before the release of WWDC. And I think we share the same vision about the future of language model. The idea behind it is like we construct a graph of a language model where each node represents a specialized model, and the edge is used for information transfer. Yeah, I mean, this idea is very similar to graph neural network. That is like each node represents some information, some entity, and the edge is used for message transfer. Yeah, message transfer is a standard terminology in graph neural network. And the idea is like we make an analogy of our model, this graph of language model, to the distributed system. So in a distributed system like a Kubernetes, you would see the master node and the worker node. I mean, in Kubernetes, they call it pods. But here, I mean, we can use the node here, like, so the idea is like, rather than one huge model like GPT-4 doing every task, we can actually use a specialized model to do the work. From the community, we already seen like a specialized model can outperform GPT-4 in specific tasks. For example, we've seen like a low GPT from Harvey AI, and also there are medical GPT, and also there are math GPT, physics GPT, which exhibit really good performance. For example, the DeepSeek math model. So what if the specialized model can do the work very well? Why not use a smaller but more environmental friendly and efficient and cost friendly model? rather than the big GPT-4 model. And in a real use case, user can propose different kind of query. So what if we can have a very good router, kind of model router to pass the user's query and identify the best specialized model to fulfill the request. And then we will have a distributed system. It's like, you construct a distributed system to compete with a monolithic big computer, that kind of idea. So the generation stage is still very similar, but now the model behind it is the G, which is the graph of our language model, and then there is still user querying queue, and you need to get a result Y, which is the response or our action output, and rather than the function selection, you actually now have a graph traversal. So basically, you want to use a graph traversal process to fulfill your request. Maybe you have a really complicated request, and you send all these requests into our graph of language model, and it will fulfill your request by using different kind of specialized model. So there will be a work path inside this graph. And if you split the probability expression here, you can find like this expression, like based on each node, based on the master node here. This expression is very similar to our expression here, and that's actually an Octopus v2 pattern problem. So the idea behind it is like you have a graph of language model, and now there are some nodes for worker node. These worker nodes are specialized model, and our Octopus v2 can be the master node. It can redirect users' query to a specific specialized model, and it can rewrite your query. That's also the magic part of our graph of language model, and it sets it apart from other model router paradigm. So here is an example. From a user, it may ask a very natural question about mathematics, like tell me the result of derivative of blah blah. And then the response is a function token, Nexa 4, can map to the math GPT. And now you got the right specialized model. Again, this model is also open sourced on HuggingFace. And you can also search it on Twitter or LinkedIn to see more posts about them. It can not only find the correct function or the correct specialized model, it can also rewrite your query in a format that is suited for the specialized model. So it becomes like determine the derivative of the function at a certain point and interpret the result with a certain blah blah here. So it basically like reformat your natural language query into a professional math query. Similarly, if it is a medical question, it will convert your medical question into a very professional question. It's like there is a translator, between your question and the real question or the professional question. Because for MathGPT, this kind of query is more common in its dataset, and that can improve the result. So this is the demonstration of our graph of language model. We call it OctNet, and this is also an Octopus. So it taking the user's query, and then we convert it into, if it is math GPT, so convert it into math query. If it is a low GPT, becomes a low query, or it's health query, coding query, or design query. And we found like using this way, in each inference stage, we can only use 2 small language model, which add up to around 10 billion parameter model. We can achieve an MMLU score of around 74. That's over GPT 3.5. And I love a comment from HuggingFace from the community that is like our model can be seen as a mixture of models. So if you look at currently the best I think the best architecture is a mixture of expert. That's actually an implicit router. It's token wise router. But it actually even inside math there is multiple subject and multiple classification. So we kind of introduce like a mixture of model method, and it can be combined with mixture of expert to deliver deliver better results. Yeah, this is the MMLU score of our model compared to other model with the same parameter level. And the use case for this model is like, you can deploy our Octopus model on your mobile phone, and all of your query will be processed, locally. And then there is a cloud server. The cloud server is not a big giant, GPT-5 or 6, that kind of big model, but thousands of small specialized model. They're working together to fulfill each request that you send. And we can use, we even, demonstrate this kind of system design in our paper. So we can use Kubernetes to do the load balancer, and we can use Redis to save all the chat history for the KV cache. Another work we did is called Octa Planner. So, in a typical GPT-4 agent workflow, what it did is like a typical React framework. React is a pretty famous framework for AI agent. And what it did is like, there is action and observation. So let's say let's say if you use GPT-4 for AI agent workflow, the process is like, firstly, you need to provide a function description. And after you prepare that, you put all the function description in the context. And then you get the user's query. And what it did next, let's say you use Assistant API from OpenAI. It did is like, it will decide which action to take firstly, and then it will get the observation of this action output, and then do this iteration loop until you get the final results. So we found like a small language model cannot do this kind of really complicated workflow. The model we just introduced is an action model. It cannot do planning multiple times, but we found another framework would be very effective to do this totally on device, which is a planner action framework. That means like we use a separate model for planning and a separate model for action. So as you can see here, if a user gives us a really complicated query, we can send it to the planner, and the planner will, output multiple steps, step 1, step 2, step n. And then we will use our Octopus model to execute each step and get the observation and pass them until you get the final answer. So this is also a paper. You can search Octa Planner, and I believe there is also some Twitter about it. For example, from MIT CS and AI Lab, we actually collaborate with some researchers from MIT about this work. This is the demo for Octa Planner. So let's say you have a really complicated, query, which is check news and find videos about Jason Huang from NVIDIA, and then email both to a certain mailbox. And of course, this task cannot be fulfilled by one single API. What it did is like we kind of split this task into 3 different sub-steps. the first step will be check news, search for the first step will be search for news about Jason Huang, and then search the videos about them, and then email both. As you can see, we can still achieve a very low latency. And Octopus V2 will execute each command one by one. Here, I would like to add some background about the way if you use the OpenAI solution. According to our evaluation, each agent call if you use OpenAI GPT-4 API, the cost will be 3 cents. That's actually a lot. If you want to use AI agent in your operating system, you can expect hundreds of usage of this API call. That means every day you may have many calls about the agent call. I think there is some question in the chat. Yeah. Thanks. Yeah, help to answering the question. Yeah, you can send the question in the chat, and that can also help to answer the question. Yeah. So additionally, we have our very recent model called Octopus V3, which is the demo we just showcased, and it's a very compact model, less than 1 billion parameter model, parameters in a multimodality model. And it can be fluent in both English and Mandarin. It can have the same level of accuracy as GPT-4 in function calling, and it can process both text and image for function calling. Next, I would like to introduce Cora SDK, and our CTO Zach will introduce this part for you. Zach, maybe you can share your screen so that it becomes more convenient. And again, feel free to ask any question in the chat, and I'm happy to answer the question.
Sure. Thanks, Alex, for the great mathematics and theory explanation. So now I'm going to show you more on our go-to-marketing production and our demos for Octopus model and the AI infrastructure. So as you notice that we have very good the models that can run efficiently and on device. But at this moment, there is no standard on-device inference infrastructure on the market. Currently, in the open source community, Llama CPP is the most popular one, but it still has a lot of performance drawbacks, especially for GPU, and there's limited support for NPU. And we, Nexa AI, we have working on Cora SDK. The Cora SDK is specifically designed for efficient on-device LM inference. We have achieved 20 tokens per second prefilling and decoding speed on Samsung S23. And our infra supports full range quantization from 1.5 bit to 8 bit. And it's supporting multiple platforms.
Zach, are you sharing the screen?
Yes, let's try one more time.
Can
you see my screen?
Yes, it works now.
Okay, there was some drag. Thank you. Thanks, Alex. So for our Cora SDK, as we mentioned, it can support multiple platforms, and it can support CPU and GPU hybrid inference. So let's take a look at how fast it is in a real example. So in this example, we are using Samsung S23 with Snapdragon Gen 2. And as you can see here, we have turned the internet off in airplane mode, and everything runs exactly on device. And we have the model deployed locally. And now when user says, take a photo, you can see that within 1 second, the decoding starts. We have achieved a time to first token performance of half a second. And our decoding speed can achieve 20 tokens per second, which is blazing fast. We will show you more demos in comparison with other open source frameworks soon. you can see that the total inference is just 0.3 seconds, which is instantaneous. And then the user can send an email to a specific receipt. And now you can see that the email contents is outputting blazing fast, like GPT 3.5, and the total inference is less than 3 seconds. And this exactly suits for the usage of users on a device. And then let's take a look at the next one. So in this example, we benchmark our inference structure with other popular open source ones, including Llama CPP and MLC LLM. So as you can see here, we use a very cheap Google Pixel 6 phone. It was released 3 years ago, and the phone is roughly $200. And the middle one uses our Cora SDK. The left one uses MMLC, and the right one uses Llama CPP. The three of them both use the Phi-3 as the same benchmark model. And let's say the user types something, and you can see that the middle one is our performance. Our time to first token is almost instant, with less than 1 second. And now Llama CP just started. To get a better look of our demo, in the next a few seconds, you can see that we have do the mirroring of our screen to show you a better resolution of what happens on the screen. So here you can see that our model, our inference structure can achieve like 800 millisecond time to first token. And even on such a low-end phone, we can achieve roughly 8 tokens per second inference speed. In comparison, even after our inference has finished, MLC hasn't started yet. And that demonstrates our superior time to first token capacity and our decoding speed. And we are rolling out this infrastructure very soon to developers, along with our next product. Beyond that, we have also enabled very low-end compute engines like Raspberry Pi. As you might notice, Raspberry Pi is a very low-end computer with just 2 GB memory. And we can compress our model to make our Octopus model work on Raspberry Pi. As you can see here, the internet is fully off, and we have connected the Raspberry Pi with this monitor to show you what's happening underneath. And let's just take a look at the email example. So in this example, again, we ask the model to write an email, ask for collaboration. You can see that even on Raspberry Pi, after quantization using our infra, the model can achieve roughly 8 tokens per second inference speed, which is very satisfactory for the on-device usage. So beyond that, we have also expanded the capacity of our Octopus model to support end-to-end voice in action out scenario, such that the model can work on like to fulfill our customers' request, like the wearable devices and the car usage. So as you can see here, in those examples, the user asks to take an image, and the inference is still pretty low with our new model. It's just takes like 0.2 seconds. And when the user will ask for a search for Taylor Swift on YouTube, this audio, the end-to-end solution just takes a quarter of a second. And this model is less than half billion parameters, which is our up-to-date model, and that can fulfill the instant on-device usage. Yeah, you can see that our most up-to-date closed source model for Octopus V2 can achieve a latency less than a quarter of a second, which is a major update we have achieved recently. So going beyond that, our model is not very popular among enterprise. Also, a lot of developers from open source community, they use our checkpoint on HuggingFace and create their local LLM controller on different devices. For example, in this case, a developer use our checkpoint to control the Mac OS and send an email. You can see how it works on his local laptop. And we encourage you to try our checkpoint on HuggingFace or contact us for further collaboration. And going beyond that, since our model is a multimodal model with vision capacity, so our V3 model we have successfully embedded on wearable devices such as Meta Quest 2. So in this example, this is a live demo. And in this example, the user asks design a living room for me and evokes the functions to design the living room, generates the panorama and virtual environment, and we can do the multi-round conversation. Then the user asks he wants a pink sofa. And then you can see that the pink sofa is generated by evoking the generate furniture action. And then the dim the light action is evoked after the user say the next query. And then the user wants to change the environment and say, go to the Tokyo city. And then the next action is evoked. So one interesting part with this demo is that in this virtual environment, you can look at the space like this Tokyo station and say, tell me about this building. You don't have to emphasize what building this is, but our model has the vision capacity to interpret it and pass the correct arguments to Google search and evoke the Google search in your VR headset. So we are actively collaborating with AR, VR device companies and embed our model to more devices. And we probably will see our device, see more devices using our model very soon. Going beyond that, so we also can make this model as a personal assistant on different form factors. And in this example, it shows that the model has the personalization and learning capacity and also do the planning for you. So in this example, you can ask, find where the Nexus party is, book an Uber there, and then tell Alex the ETA. And this is a multi-step example. And with our Octoplanner model, it can break down the task into multiple subtasks and then evoke our Octopus action model to trigger the action, call the Uber, and send a message and fulfill the workflow for you. You can see that the message first is sent to Alex, and then you can see that after receiving it, it gets the observation and then book the Uber according to the observation information. And then the whole observation is then passed to the third action model and the message is sent to Alex. Yeah, so those are the demos which demonstrate the capacity of Octopus model on multiple form factors. And the most exciting thing is that we are collaborating with HuggingFace for a hackathon together soon on August. So if you are interested in AI agent and on-device AI model, feel free to scan this QR code and join our Super AI Agent Hackathon. And we will host this hackathon in a multi-way. We have the online version, and if you want to come to the on-site, we have the final computation at Stanford Research Park. And feel free to scan this QR code, and we look forward to see you in person or online. Thank you.
Thank you so much, Alex and Zach. This was a fantastic presentation. We can open it up to Q&A now. I see a question in the chat. From Igor, do the users need to provide their login credential to Uber or their email?
Yeah, I've answered the question. Yeah, just Uber has a developer platform, so there are different API relevant to their application. So for a certain user, you need to provide your login credential so that the API operates your account, but it's just one time. Yeah.
Great. And I'll open it to anyone else. Feel free to unmute yourself and ask any questions. I could start it off. Can you tell us a little bit about how Nexa started?
Yeah, we too are kind of, already have like entrepreneurship ideas in mind. So we too are actually actively involved in a Stanford Student Entrepreneurs Club, and we both served as president of that entrepreneurship club. And during that time, we actually, get access to many like opportunity to meet with investors and entrepreneurs. And I think around 3 or 4 years ago, we began to explore a feasible idea to as to work and to be and ready to be an entrepreneur. And after that, I think after the rise of generative AI and transformer and diffusion model, I think every machine learning researcher should be very excited about them, because they really introduce a unified structure to process a lot of data. And then as expected, there are many new opportunities coming up. And um, and we think like we should also bring this kind of powerful ML architecture and its capability to edge device. And we found like it can actually change the operating system or the whole software ecosystem in edge device as well. So that's why we began our company and choose this certain direction. Yeah. So I guess I found additional question. Have you tested the impact of reducing the model size in terms of reduced robustness? Does the smaller model hallucination more frequently? Yeah. So the critical part of our model is like it's a function calling model. So that means like we actually adjust the parameter or fine tune all parameters so that it can be it can specialize in a certain task, which is to serve as a model for AI agent, not for general question answering. So even if we reduce the model to 500 million, it's not 2 billion, 500 million, it can perform pretty well in the hallucination or the robustness. Because when you design function callings, you can set a lot of like default value using this kind of tricks. You can greatly reduce the mistake. And is there a feedback loop built for this? Yeah, I mean, when we like build our model and test it in product, right? There is a user's feedback, like a user's result, and if the user give us the permission to improve our model, we will collect this kind of data to further fine tune our model, and this data can also be pretty helpful for our model. Yeah, so there is a feedback loop.
We have another question in the chat. What kind of pre-deployment safety testing do you do?
Let me. Yeah. So the safety check is like the tricky part is like our model can only perform in a certain set of functions. So as long as you did a safety check on the function set, it won't output other unexpected result. So for example, inside your mobile phone, there is only, let's say, 1,000 APIs available. And it's pretty easy to check these 1,000 API, whether there is some dangerous API. And we also set another additional API, which is called irrelevant function. So if you say something, not considered as a good use case, we will return you as a irrelevant function. So you will won't answer to or give meaningful result to some dangerous question or prompt.
That makes sense. We have another question. Do you think using AI agents is largely just prompting with automating what the agent answers, or does it involve other things as well?
Sorry, can you repeat the question?
Sure. Do you think using AI agents is largely just prompting with automating what the agent answers, or does it involve other things as well?
Yeah, I think agent usually, includes I think the two important part, which is planning and the action. So it's like a user give a prompt input. I think a more straightforward way is like this. So the output one is a very determinant, which is the action and the result of action. But the input one could be multimodal information. It could be audio, text, image, or video. And then the agent should be able to do a planning, like to fulfill your task. And there could be multi-step. And then for each step, there should be an action model to fulfill that action sub-step task. In my mind, in my perspective, I think that's the AI agent. Basically transform, the natural language instruction and other modality information into a final result that can fulfill your query.
That makes sense. Thank you. Another question from Igor. Could you please share the sizing footprint parameters and minimum requirements for smartphone on-device performance? For example, minimum disk space or RAM required to run your model and SDK on smartphones?
Nick, would you like to answer this question?
Yes. So right now it works on Raspberry Pi with 2 GB RAM. So we expect that any mobile devices stronger than Raspberry Pi will work. And for the demo on iPhone, so our Core SDK can support Mac OS and iOS operating system, and we will roll out the iPhone demo soon.
Yeah, the demo we just demonstrated is on Samsung phone. Yeah, actually, there is a wait list on our website, nexaforai.com. So everyone, who are interested in this domain can subscribe our, maybe newsletter or subscribe our mail list. We will have very exciting, open source work to release this month. Yeah.
We have another question in the chat. Do you have any experience or advice to share with folks who want to do a startup like you?
Yeah, I would encourage we believe this may be the last chance to do a software entrepreneurship because AI can really transform the software a lot and can replace the typical software service. So if you want to be an entrepreneur, just do it and don't wait. For example, when Zach joined me as our company CTO, he's a Google engineer with really high salary, and at that time we have nothing, and we also raised nothing. But he just dropped out. He quit his job, and we started this company together. And I think since and hopefully we've created something meaningful. Yeah.
I have one more comment here. So we're actively hiring. So I also add our career page, Alex and my email there. If you are interested to do the research on generative AI, on device AI model compression, or you are more interested on engineering or product management or enterprise sales, whatever you're interested in, feel free to contact us.
Yeah. And we actually just raised a pretty considerable amount of fund. So we are actively expanding at this time. Yeah.
Awesome. I hope a lot of people check out your careers page. We'll ask the last question. Thank you again for coming. The last question is, how does the Octopus model handle situations where user intent is ambiguous or requires disambiguation?
Yeah, so that's relevant to our next generation of model. So we found a way to save your preference in a certain format. That is like now you have the on-device AI model. So it's not like GPT-4. It's hard to imagine you have billions of models on server, but everyone can have one model on his own phone. That means we can do a lot of work on this phone, and the model weights on your phone can adapt or can evolve according to your preference. So it can understand you better and better. For example, if Zach and I ask the same query, like tell me about iPhone, maybe I care more about stock of iPhone. He cares more about the latest model of iPhone. And the model can actually give you different response according to your preference. And that's the work we are working on now. Yeah, so in the future, we will support, we will be able to solve this kind of ambiguous question. And that's also, one typical question from our customer, like who are really interested in it.
Fantastic. Well, thank you again, Alex and Zach, for an incredibly insightful presentation. And thank you everyone for coming.
Thank you, Abel.